Okay, so today we're gonna get into tolerancing in our technical or engineering drawing. Well, tolerancing is very important because when you do the mass production, this is going to tell you everything that you need to know about your part. Okay, and like I said, it's very impossible for anyone to make the part as you draw or as you give the specification. Okay, the specification that we get, we can never be able to produce exactly as that. So therefore, you have to give them some space for the manufacturer to make the mistakes. Okay, but everybody make mistakes. So tolerancing is kind of like giving the range for the manufacturer to make mistake, and the mistake can, all right, be able to make in that range, not below that range or not above that range. Okay, as long as you make your part in between the lower limit and the upper limit for every dimension that we do, you're okay for mass production, right? So let's take a look at how we do that. So this is writing what I've just told you about, because we're allowing the parts to vary within a range of values or limit. It's just writing it in a very formal way. So you know that there is a range, and when we do the mass production, when we produce the part that you draw from the specification given to you from the engineers or the design team, these people, all right, on the shop floor or manufacturing floor can be able to make mistake in that range. Okay. Another thing is by doing tolerancing. Tolerancing is nothing but we're just giving you the values or limits of of the range, upper limit, lower limit. Yeah, we call that tolerancing. So another thing that's very important doing this technique in mass production is that you can do the design interchangeability. Okay, you can do the design interchangeability. So interchangeability in design is very good, very good, because you add flexibility, in your drawing and also in your production. Of course, we also call that in common word is replacement parts. So by doing the tolerancing, you can design interchangeable or replacement parts, right? So this is what is written here formally. So now you know, you can't get the idea, a big idea, and we'll get into details how to do it. So here we're writing this again, in this book. So tolerancing is dimensioning, putting the values. Of course, dimensioning is for interchangeability. So when you think about the interchangeable part, we're talking about a replacement part, okay, for mass production. I mean, these parts are not different, they are the same, right? The same size, the same part, but there is a little bit of variations with it, and we call that interchangeability. Okay, so let's get into our replacement part, so interchangeable part with tolerance. We're going to take a look at how to put the value, dimension, meaning putting a value to the feature on that part. Since we're doing tolerancing for interchangeable part, your exact single value dimension is going to become the range values. So here single value is 1.00, then when we range it, we give like, that value can between 0.995 all the way to 1.005. So 0.005 above 1, and then 0.005 below 1. All right, so this is what you can see the range, and of course your ideal dimension value is in that range. So when you take a look at it, this we call it, that's the amount of size variation permitted. So we call that tolerance. Of course, depends on what you're doing, what you're producing, your cost analysis, everything, all the factors that is important to your manufacturing. Okay, we will consider that usually come from that tolerance, how big or small the variation you allow in that range. Okay, that will also identify the quality value of your parts as well. Yeah, so manufacturing is a business actually. Yeah, making money, massive amount of money by producing incredible amount of numbers of of the same part, yeah, or same product, because people want it, and there are so many people in the world. The population is, oh my gosh, in billions, right? And everybody wants a cell phone, things like that. So anyway, so yeah, the mass production is really very is a huge thing, and that's why we call it industries, all over the world. We're just taking everything for granted, at the house, at your house or apartment or wherever you're living. You have so many things. They all come from manufacturing, mass manufacturing, okay, from the factory. So the tolerance is a basic, for making money at the end of your mass production. So it's really important how you make that range big or small, because your Six Sigma, right, values to increase efficiency of profits and things like that. So all the business calculation of factors depends on this tolerance range, okay, and of course in production. So tolerance, if we want to put it in mathematical expression, you have a maximum size minus, and you have a minimum size. So this is your max size, and then that's the min size. So when you take a look at an example, here is the example again. Here is your maximum, and then here is your minimum, size. So that's tolerance. Of course, when you subtract it, you're gonna get the subtractive value. Okay, so when you take a look at this, we can calculate it quickly, and you get, so 1.005 minus 0.995, and you're going to get 0.01. But this is just a roughly, loosely telling you, but there are many different kinds of tolerance, right? So it depends on how your problem or the situation identify what's the maximum size and what's the minimum size, yeah? But most of the time we don't do this calculation. We usually just go with the upper, and the lower limit like that, a range. We call it a range, like I say, a range, okay? And of course your mass production can for each part, whatever you're producing, is allowed to vary in that range. Okay, meaning like allow you to make mistake away from this ideal value 1.00, but not under 0.009, and also 0.995. Sorry, what am I saying? So the lower limit, and you can go all the way to 1.005, but not more than 1.005. Yeah, so your idea is right here at the middle. So every part size is now, it is controlled by two limits, your upper limit and then your lower limit. Yeah, so it's a very important, and it's to know that it is impossible, for us to manufacture parts without some variation. So we allow that variation between the two limits. Okay, so these stated limits are very important because they are a form of quality control. Yeah. So when we choose a tolerance for the design, so what kind of tolerance should I come up with for a particular design that whoever wanna, your producer or or investor wanna make, everybody gotta go in and try to make that happen. And of course, so we look at the cost experience, we look at how it is gonna be manufactured, we look at the design intent, right? Intent meaning like who is gonna use that product, of that part. So these are everything that we think. Of course, this is like a grand points here, 1, 2, 3, 4. But in reality, doing this is taking a long time. Even for cost analysis, it takes like like a quarter or 2 quarters, because you got to look at the historic data from the customers, and of course you have to calculate. And it's always continuous improvement, because every quarter, you have 3 quarters in a year. And people just want things, and they always change. Nothing stay the same. They want this, and they get bored and want something else. So all of this design intent is always changing. Never stay the same. Everything is always is yes, going depends on the desire of the people. We want too much, and since people got people got to make that happen. It's a lot of a lot of work, and of course, so we make us busy. That's why we call it business. Doing all the manufacturing that there's in the world to serve what people want to get. Of course, every time we deal with the manufacturing, you should know by now we need the standards. We always follow particular standard, and you have already studied different standard bodies. So it depends on the company. They're going to choose and follow one of these standards, and you study, of course, and design your stuff according to these standards, including tolerancing. So by following the standards is very convenient for us, for the manufacturers, because they can be able to manufacture their parts at different times and different places. You can assembly the same way because you're following a common standards. And of course, for tolerancing, we've got the limits, your dimension limits, for these parts, for replacement parts, which are very interchangeable, comes from that limits, again, your range. You're not just making like whatever you want to do. Even if you're making the dimensional limits, you still follow the standards. Why? Because you can make parts different times at different places. Of course, the lecture presentations are not the same. We always use a black and white because it's very easy for us to print the handout that way, because we can put all the pictures that there is in the world like outside presentation. Okay, so you just have to follow the lecture. Taking the lecture you have to come to class, or of course we're doing a virtual lecture here, so you at least need to listen to it. You can just look at the pictures and getting it. So anyway, two most common standard agency: ANSI, ASME, ISO. This three, right? Standard body, you have to get it. Okay, so ANSI, again ASME, and your ISO. This is your International Standards Organization, and that's your American National Standards Institute. Okay, American Society for the Mechanical Engineers. So this is our group, and you have to be be in touch with these groups. So go ahead and get their website and bookmark it. You can go in the browser, look for it. Of course, I'm not going to show that. There's a wasting my time here. Which you can do it at your home. We're not going to go in and look and show this website. It's your job now as a university or college student. You have to back up every 1 hour of lecture, 3 or 4 hours of your time to actually doing assignments and studying. University is very different from high school. High school have time for doing assignment together. But for university, the amount of knowledge you gotta get is too much, which you don't really use all of them when you work, by the way. But you need that foundation for you to grow, meaning like for you to get promoted and don't get stuck at the same position for a long time, So that's why the basic and your foundation knowledge, you gotta get it when you are a student. This is the only time you can get it. Of course, you can develop a little more and more if you have time in your life, in the future. So anyway, at least get these three groups. Standard agency, Then we'll get into our tolerance types. So the tolerancing methods, we have three. One is called the limit dimension. The other one is plus or minus. Some people write it like plus dash minus. It's the same thing. A page, dash block, the same thing, page or block tolerances. So these are just a name. We'll get into it one by one, in the lecture. So the types, why do we have three different types? Because not all the parts are the same. So therefore we need, this is the three group that you can come up with to to be able to tolerate many different types of parts. Okay, so that's your method how to tolerate these parts. So three major methods: limit, plus or minus, page or block. Okay. All right, limit dimension in value wise looks like this. Of course, we put symbol. It depends on the symbol. In this example, I'll put in a font, so you're dealing with a diameter, and you know that. And here your maximum and minimum. Your min here, your max right here, your min, and then your max right here, right? And that range is okay for your quality inspection pass. As long as you stay in that range, you're okay. You can make mistake in that range, right? So that's your maximum and your minimum size for the part you're working on, of course. So here, in this example, your part is a shaft, here, and then of course your tolerance limits are for the diameter. Why do you know it's a diameter? Because of the symbol, and don't forget to review the symbols. Here, from here to here, just telling you very formally where the limits are. So here is your min, and that's the max, and that's how we write it, linear. This one is a vertical, so that's your min, and that's your max, and that's how we write it. Okay, so pay attention to this decimal. See that? Some students, especially international students here, like reading and then they go crazy about it. This is just showing you the low limit precedes the high limit, meaning like we write the low limit first and then followed by your high limit. Okay, and you don't have to write many different ways either. You can just go with max and min, or upper and lower, low or high, depends on whatever you want to do. I just go with the upper and the lower. Sometimes I go max and min, so it's up to you, whichever way you wanna. The next one is your plus or minus tolerance. See, like how we write, very different. So I'm going to show you the very first one so you kind of see the differences. So the very first one, see, like the very first one for the limit, see? Very particular way of writing, okay? No plus or minus. Now, plus or minus, we're using plus or minus right there, sign. See that? So here is your idea. And then we can go 0.1 up and 0.2 down. Different range of how to write. Some of the ranges are perfect, perfect value going from the ideal value. They go the same, alright, value down and the same value up. This one, see, only 0.1 up, but 0.2 down, okay? Mostly they're equal, but sometimes you're going to see odd, alright, ranges like this. But don't freak out when you see it like that, it's okay. And because it depends on the part you're making, okay? So plus or minus tolerances, always give you in the description, description when we write plus or minus tolerance method, we usually give the basic size. So this 10.1 is your basic size, and then of course your variation here. A basic size is not given in limit dimension. Okay. All right. Then we'll get into page or block tolerances. Page tolerance, you already knew that. We already studied in the very beginning. It's just a general note, and you can be able to see the tolerance here. So that's called the page tolerance method. We're giving in our drawing to the manufacturer what to do, with the parts. So page tolerance, we use it to cover everything that we didn't mention in our drawing, And block tolerances, they're gonna be in the block, of course, and that's the same thing, page or block. Block, we call it block, it's because we box it. We call it page because we put it on the drawing canvas, which is your print, of course. Your review, your tolerance block is to the left of your title block, and above your projection block. Yeah, so that's, you can see it in the print. Okay. Okay, so in this book, of course, the author is using the shaft and hole assembly as to teach you the tolerances. Okay, so we'll get into different concepts and also different definitions. Yeah, using the shaft and hole assembly system. So here, this is your shaft and that is your hole. It's pretty easy to read. Yeah, here is your diameter. Okay, little diameter, small diameter, and big diameter. Okay, I'll give it to you here, and here is your center. Yeah, you know how to read them. Here is a section line because we cut. Yeah, cut the hole to see inside of it. Okay. Then first we'll get into inch tolerance. Inch tolerance, so when you take a look at it, you can quickly identify, oh, this is inch tolerance that I'm dealing with by looking at the decimal. Yeah, there's no zero in front of decimal, because that's the way American writes. All right, the SI system, you always have to use a zero, but Americans, they don't want to write it. Okay. I study science a lot, so I follow the SI system, but it's okay. Yeah, using the British or English system in America, like you always do. But be very, very careful when you deal with the drawing if you want to keep your career in this line. It's because the common mistake, that costs a lot of money in production, because you're doing the mass production, is that little decimal right there. Okay, so 23 and 0.23 is a big difference. Trust me. Some of the engineers, some of the designers, some of the CAD, okay, drafting people, they miss it. Okay, because people are all stressed out, and people get fired, of course, because of this little decimal. Okay, so even though we follow, of course, the inch tolerance with the British or English writing system, be very, very careful, and you will have to double check, you will have to triple check, quadruple check, group check, check that little decimal. Okay, so I am pointing that out by taking about a minute to you, so you remember, when you work on some projects. Okay, so let's get into the tolerancing method. So first you gotta know limits. Your limits, your max and min, of your part size. Your max and mins are allowable, values, and we usually put it in a range. And then your basic size, we usually use the basic size to calculate the maximum and minimum limits. Okay, so it's really important. So if you're given limits, I'll show you how to calculate basic size. If you're given basic size, then you should be able to calculate the limits. Right? It's pretty easy. Now here in this book, we're using the hole and shaft system. So it's very common for both your hole and the shaft. You will have to use the closest, all right, closest fraction every time you deal with the basic size. Closest fraction meaning like if you doing the decimal, then you round it down, like that. All right, so tolerance. This is just a formal, definition. That's just a total amount of your values or your specific dimension, which is allowed to vary. Okay. Just remember the range. Don't go outside of that range. You can be on it, but not outside. And the next one is your MMC. That's your maximum material condition. Max material. Remember these two words. Max material means you're left with the most of the material. So formally, it's the size of the part when it consists of the most material. Least is going to consist of the least material. Meaning, we'll show you which is MMC and LMC. But right now, for definition, know that maximum material mean max material, least material mean the least material on the part. Okay. All right. Maximum clearance. Maximum clearance. You can calculate this way by taking your LMC, your least material condition of the shaft, out of the least material condition of the whole. Yeah. Minimum, you're gonna take maximum material condition of your shaft out of maximum material condition of the whole. Okay. And that's your minimum clearance and maximum clearance. A lot of the people also have confusion on this, so make sure you study before you go out to work. Because I don't know, some of the companies I have visited, some of the companies in Mississippi, and so many people working there, they don't really know what they're doing. But I don't know why there's a big disconnection between the human resources and the people who are working. Okay, I don't know how to tell you what that is. Probably corruption of some sort. So human resources, ladies or gentlemen in there, don't really understand, the subject. So when they hire people, they're hiring by reading their transcript or resume, and it just very very difficult. Or I don't know like how difficult the human resources processes are, but they seem to be placing the people in a wrong position. Okay, they don't. A lot of the people get the job but have no idea how to do it. And when you and I want to, like in my research, I want to go in there, operations and management, mention things like that, and visit them to see what's going on with these human resources. Why are they always choosing, like they would choose a chemistry major, and the chemistry major became the supervisor of the quality control in one of the company. I was so surprised. Yeah, however good the person is to manage, right, still lack the knowledge of the engineering aspects of it. So I'm pretty sad about all of that, because people who come to school, study for degree, doesn't matter associate degree or full degree, all the way to masters and PhD, and they never get a job. And they happen to be like doing the work under chemistry major or English major, sometimes like history major. I don't know what to say that either. So we do have a serious discrimination and also serious corruption in the human resources, department or whatever. I don't know, but just prepare for that. Yeah. So when you go in to work, you will have to deal with different kinds of people who is not going to be seeing the same thing like you do. Yeah. As you learn from school, and sometimes they will go back to school to learn because they know, oh, I'm not, doing the right job, and somebody, recognize that, things like that. So if you do know, just don't say you will lose your job. And I learned that from my experience. And of course, when you were young, you tend to talk, and I am teaching my student, don't do it. If you want to keep the job, just go with the flow. Go with the flow, okay? And you have to learn that in addition to the subject, okay? Even if you know the subject, don't show too much that you know, because there are so many people around you who don't know and who just don't like that you know, and you can recognize their deficiency, okay? So I'm teaching my student to be very careful when you start your job, okay? And if you are one of them who don't know and doing that job, make sure that you take your time to learn, learn and correct about it, because it can hurt in manufacturing world. Of course, one mistake can hurt so many people, including your life, or your career. Okay, so let's go back to the next one. Alright, so this is our first example, and you have your shaft and hole system right there, and you're in inch tolerance, by looking at this little decimal without the zero, you're in inch tolerance, and it said it so here, So we will fill in everything that we know, So limits we can quickly write your shaft is here, yeah, your hole is right there. So 0.47 and 0.51, this is easy. Yeah, all you have to do is write the minimums and the maximum. The basic sides, you have to calculate it. Okay, so how do we calculate the basic sides? So here I gave you this handout. It's up there. Yeah, you can download it. The same thing. So your upper limit. Okay, so here is your upper limit, and then the lower limit. So you're gonna write that down. So we start with your shaft system. Yeah, you're gonna put it, add it up, divide it by 2, and you're gonna get 0.49. Okay, so then you write this here. Yeah, a basic sign is for a shaft and hole, so we're going to calculate the hole as well. So we go down to the hole, yeah, 0.5, add it up, divide it by 2, you're going to get 0.495, see? 49495, so therefore we are going to get 0.5, yeah, for the rounding. Then we will calculate the tolerance by... Then we will go into tolerance calculation. So here, yeah, you can read it here in your Excel sheet. I gave you this Excel calculation as well, so you know how to calculate it. Yeah, basic sides, each one of them. See, and this is just getting the common, yeah, in between your shaft and hose system. So here, the first one 0.04 because you're minus, yeah, 0.51 minus 0.47, and this one 0.5 minus 0.49, you're gonna get 0.01, which is here. Yeah, then we have to calculate MMC and LMC. Yeah, and once you get this, you're gonna do this. Yeah, LMC, this is your clearance. MMC, right, you're gonna get the most material. So let's see how we calculate that. I'm gonna go back to my Excel and show you how to do it. So MMC, the maximum material that you have to get for the shaft. So when you take a look at it, the maximum you can get is the upper limit, yeah, so which is 0.51. See that? And for the hole, the maximum is going to be 0.49, yeah, because that's the maximum that you can be able to get, yeah, because this is the whole material. So if you go with 0.50, you're gonna get the least material. If you go with 0.49, because this, see this space, so that's the diameter of that. You have to choose the smallest diameter for you to get the maximum material, all right, in there. Okay, for hole is a little bit difficult for you to understand because you think like this part, okay, the part of the hole is the material of the hole. No, the part of the maximum, okay, material condition, meaning the most material gotta be on the part, okay, not how wide your diameter of that hole is, right? So pay attention to that. So that's why we put like 0.49. Least material condition again for the shape is going to be 0.47, right? The lower limit. Again, the least material, you gotta understand that we're talking about the material on the part, okay? It's the least when you have the smallest diameter of the shaft, okay? Why? Because we consider both of them, yeah? Material condition is for the part, not for the shaft or not for the hole, okay? How wide the hole is. So you have to consider both of them. So most material will be left when the shaft is the biggest and the hole is the smallest on the part, okay? Least material will be left on the part when the shaft is the smallest and when the hole is the largest, okay? Again, least material and most material you are considering on the part, the material left in the part. So pay attention to that, okay? You might not get it right away. It might take a week or two, I guess. Some student will take some more time to get that in your brain, okay? All right, maximum clearance is easy, yeah, to calculate. So let's go back to Excel. And here all you have to do is just take maximum hole minus the minimum, right, shift. This is S for shift and H for hole. So 0.5 is your max for hole, 0.47 is min for shift, and minus it, and you're going to get 0.03. Do the same thing, okay? Do the same thing for the minimum clearance. You're going to get that. So how do we get this? So we take minimum hole minus the maximum hole. Since the maximum shift, okay, has more value than the minimum hole, you're going to end up with a negative value, okay? And of course, we're going to put that in here together, okay? I give you this because some students have frustration last semester because they were putting like 0.495 and never get the correct here. Yeah, so you have to put it in this way for you to get the correct in your, the website that I give it to you to practice. Okay, so let's go to the next one in inch tolerance. Then we'll get into 4 types of fit. So we have clearance fit, interference fit, transition fit, and the line fit. Okay, so these are the 4 major types of fit. So let's take a look at them. So clearance fit is talking about space. Okay, so there's always a space. We always have space, and we always have to deal with the space. And clearance fit is nothing but your minimum clearance got to be, okay, greater than 0, and we call that defining the space, okay, and we call that anyways a clearance fit. Just remember that the minimum clearance is greater than 0. When maximum clearance is less than or equal to 0, okay, you don't have a space, and we call that interference fit. So you have to think about your shaft and hole system right there, yeah? So when you have your maximum clearance, then you don't have a space, like that's very much, yeah? So interference fit is kind of like meddling. It's like you don't have that much of space, yeah, in between. This one is you do have some space, okay, because your minimum clearance is greater than 0. So if you forget about what's the minimum clearance, yeah, you can always go back to here, and I'll show you. Yeah, so your minimum clearance and maximum clearance is right here where I put it. See, the maximum material is a minimum clearance. So maximum clearance is your minimum material. Yeah, so where you play with your maximum hole and minimum shift. All right. So that's how you get it when you deal with the space here. Yeah. So if you forget about it, you might want to go back and take a look at that. Yeah. So what I want to say is like you have in your part your minimum material because you have a lot of clearance there. You have on your part maximum amount of material on your part because you have a very a tiny little clearance in the spaces. Yeah. Transition fit. It depends on the size of your shaft and hole. There could be space or there's no space, right? And of course, you have a minimum clearance less than 0, maximum clearance greater than 0. Again, don't confuse, okay? Transition is the opposite of your regular clearance fit, which is minimum clearance is greater than 0. Here, minimum clearance is less than 0, okay? This guy is your max is less than or equal to 0. Here, your max is greater than 0, okay? So probably if I were you, when I was a student, I would just write them down, yeah, and I put them in a quarter, yeah, and try to see like what they are. Of course, nowadays tests are very easy because they make the program very easy for. I don't know why and what's going on in this. Today's students are very difficult for them to be able to study, yeah. For us it's very easy, for us to study. I don't know why. I think people get stressed out, I guess, nowadays. I don't know. So anyway, so you don't have to even remember by heart anymore, yeah. But of course, you will make your own note or use a very good pocket size, like reference book or things like that. There are many out there you can buy. So anyway, you will always have like the transition fit. You play with your max clearance greater than 0 and min clearance is going to be less than 0. Okay. Your line fit is a little bit different, and that's your max clearance is greater than 0, and your min clearance is going to be 0. So here I'm just telling you about the space between your hole and shaft. So there is a space or a contact. So that means that your hole diameter and your shaft diameter is the same. So here, look at that. This a little bit different because depends on the size of the shaft and the hole. There could be a space or not. Interference, you don't have a space, so tight fit. Clearance, there is a space. I think you kind of get all these 4 types of fit by now. Then we get into your textbook exercise. And so here, alright, so this is just a little exercise for trying to understand if they fit or they don't fit, if you have a little bit of space in between or not. So coin in a coin slot, you do have space, so that's a clearance. Key in a lock, you have space, so therefore clearance. A bicycle in the chain pin is tightly fit, otherwise you won't get any kind of movement forward. So therefore there's the interference. Then a door and door frame, there is space. A clearance, bolt and nut, you do have some space. So therefore clearance. And then your wooden pack and hammer, kid's toy, we have that because you're hammering it down, so it's pretty tight, so therefore interference. So that's pretty easy. I think I might forget to underline that in your handout, so you can just circle it by yourself. When you get that. So this one is on number 2 axle here. So you can be able to know like how we calculate it. Okay. We're just getting the basic size, for shaft, and then for here for hole, and then of course your common is going to be 1.5. So this is where we're calculating that each one of them. Okay, basic size again is pretty easy to calculate. We have to just add and then divide by 2. And you do each one of them. From number 2, 3, 4, 5, I think up to 4, 2.25, so up to number 5. Okay, so that's showing you how to calculate the basic size. And then you calculate your maximum material condition, and the minimum material condition. Write that down. And then you calculate your maximum clearance and the minimum clearance right there. So once you get the maximum clearance and minimum clearance, you can be able to decide. Okay. So after we get the maximum and minimum clearance, what we do is you have to identify the type of fit. So you're going to go back in here, and then you're going to see and determine whether they're equal to 0, greater than 0, or less than 0. Depends on the fit. Okay. And then we write it right here. So for example, first we calculate the basic size is 1.5 and type of clearance fit, okay, for the very first one. So I show you how to do that, and that's your homework. Okay, you will get 0.007 and then you will get 0.003. See that? So when you go back here, you will have to start finding, okay, what type of fit you have by looking at the zeros. Okay, so first you're going to go with the clearance fit, which is minimum clearance got to be greater than 0. So you go there and see the minimum is greater than 0, so therefore that is, okay, the clearance fit. Of course, then you will have to check whether your max is less than or equal to 0. Okay, then you will say no, it is greater than 0. So definitely not interference right there. Max clearance is greater than 0. Is a transition, but your minimum clearance is not less than 0. So therefore you look at that 2 value, and then you're going to start going over like from here one by one: clearance, interference, transition, and then line fit. And I told you what I do is I write it on my scrap paper. These are greater than 0 or less than 0, equal to 0. And then I'll put that on my hand when we calculate it, so I can be able to quickly figure out. Okay, if that's it. So this is a clearance, transition, like that. Okay. So of course I did it for you, all of this, yeah. So you can be able to go over when you study to take a look at it. And here is the Excel sheet. So you go all the way to number 1 to 5 here, yeah. So everything's been calculated for you, and you compare to your 0 here. Okay. All right. Then let's go to the next one. Then we'll get into the ANSI standard limits and fits. That's just for you to know. So what we're saying is here we go in this book, we're using the ANSI, okay? B4.1, 1967 or 1994 standard in this book. So your RC is your running or sliding, clearance, C for the clearance, and R for running or sliding, okay? Clearance fit. This is just showing you the example, yeah? So here RC9 is for the loosest and RC1 is for your tightest, yeah? And it just giving you the information for your RC, and that's your running performance with a suitable lubrication. And if you see this type of indication, you know that's kind of a loose, yeah, situation. That's a tight situation, tight test and loose test. Then we'll get into locational fits. We use LC, LT, and LN for that. Okay. Okay, so I try to fix this slide a little bit. It's too raw. Anyway, so LC, LT, and LN. So you have LC as your locational clearance fit, and then this is locational transition, and that's your locational interference. Okay, it's not LI, but LN. Okay. We call them the location fits because you're dealing with a location in your mating parts. Okay, so fits are like when you put, as you know, a product is you have so many parts and we join them. Yeah, we fit them all together. You have a form of a type of joint. Okay, joining type, and we call that the mating part. And fits are very important because if your part don't fit each other, you know, it's going to be crazy. You know, your product as a whole is not going to work. Fn is your force fits. So we have Fn, okay, 1 all the way to Fn5, so loose, and then this is your tight, okay? And of course the force fits, they provide a constant bore pressure, yeah? And that is going to be, yeah, all throughout your range, okay? You have a different ranges for that. So anyways, if you think about the force fit, you try to get like, oh, I am just having a pressure, yeah? Bore pressure. If you think about the location fits, that's for the mating parts, yeah? Depends on the location of your mating parts in your product. So try to pay attention, yeah, to these keywords. Now we come into the next example. So here's the next example. We have a basic size 0.5. We're in a British or English system, inches. And you have your RC, your running, yeah? I'm going to quickly show your RC if you forget about it. Yeah, you won't get it right away, so you just have to go back to the yes, your handout to get them, or your textbook, okay? Running or sliding clearance, so that's what this RC is about, all right? And RC, of course, 8, yeah, is going to be on this side, yeah, a little bit different. Your fit systems are. So RC8 is kind of loose, yeah? Not like here, see? This is different, going from 1 to 5. 5 is the tightest. Here is a 1 is the tightest. Yeah? Be careful, all of that when you read it, yes? In your table. So RC8, loose. And then we have to calculate the limits, yeah? Your hole and then your chef system right there. Of course, we will go all the way back to your appendix. Yeah, go to USASB 4.11967 or 2004 to get these values. Okay, and when you read it, make sure you read these tables are given in thousands of an inch. Okay, so it's going this way. So add 1,000 mean like 0, 0, yeah, 0. So when you edit, you're gonna be reading this way instead of what's given, yeah, in your table. Make sure you open your textbook. When you get to here, you can be able to get it from just the handout. And for this problem, it's not on the Excel, okay? This is on the Word. So I wrote it here, see Word file. So when you open it, you're gonna go to this page, okay, which is on page 3. So for the whole, we're gonna get our basic side and then tolerance, positive, basic side, tolerance, negative. Okay, it's gonna give you the upper limit, lower limit. So this is our definition. So we'll have to put in what we get from the textbook, yeah. And 0.50 is a basic size is given to you here, yeah. And then we will go to our textbook and read the RC8 value, and you're gonna get this too, okay. So upper limit 0.0028, yeah, 0.0028, which is here. Yeah, I wrote it there for you, and then put that in and add it up. Okay, lower limit 0.50, which I already wrote here for you. Yeah, and go back and then add it up. And of course, the upper limit 0.5 is your basic. The next reading is on here. Yeah, so we'll add them up together, and you will get this answer, which is here. Yeah. So I'll put it right here for you. So just about the limit and calculation is pretty easy because all you have to do is add them up, yeah? And don't forget the plus and minus signs when you do your reading from your appendix, yeah? For your RC8. Make sure you keep the signs, the plus and minus signs, otherwise you'll be getting a different thing. And then all you have to do is just add them up, yeah, with the signs. And you will get the whole limits, the shelf limits, lower, and then the upper. Okay, so going for whole limit is going to go 0.5 to 0.5028, and the shelf limit is going to go 0.4949 to 0.4965, which is this one. Okay. Alright, then we'll get into metric tolerances up to inch tolerances. So when you look at it, you know that this is metric because there is a number right in front of your decimal, okay? See, inches are very big, so you go by the decimal. Metrics is small because you're dealing with millimeters or centimeters, yeah? So therefore, you have a little bit bigger number, so we can be able to write a full decimal, 5.0, 5.1, 5.4, and then 5.1 like that, okay? You have the whole system in this book. Metric tolerance definition. So we'll get into your limits, basic size, tolerance, your maximum material condition, least, yeah, material condition. They have the same meaning as in your inch tolerance, so we're not going to repeat them here. So upper deviation. So upper deviation is your UD, and we can be able to calculate that's the absolute value. There are two little lines right there. It's just a mathematical formula. So I am putting a space for you, so that's not L or I. That's just absolute, yeah, symbols right there. So everything that you put in is gonna come out positive only. Doesn't matter whether that's a positive or negative inside after you calculate. So you have UD, your upper deviation, and you have your basic size minus D max. Okay. So take the permitted maximum size out of your basic size. Take the permitted minimum size out of the basic size, and you're going to get the lower deviation. Yeah, lower deviation, upper deviation. Okay, so this is how we calculate. Fundamental deviation. The fundamental deviation is you're taking the smaller of your UD. Okay, your UD, which is this guy. Okay, this one, so upper deviation. LD is your lower deviation. So for fundamental, you're taking the smaller of your UD and then the LD. Okay, so that's what we're doing. So in the symbols that we use, right, letters that we use the H, see, and then 11, and then slash C11. So when you look at it a letter in the fit specification, okay, it's going to show you the fundamental deviation, right? So this is your metric fit. we have H11 and then slash C11. These are just showing you the fundamental deviations. Yeah. Right now, don't worry about it. Okay, just look at the example. We're just going through the definition, and we will come into it in the example. And the next one is your international tolerance grade number is your IT number. We usually write it like the IT numbers. They're just a set of tolerances. And of course, when you're dealing with a tolerance, they're going to vary, right, according to your basic size and also your accuracy, okay? So when you take a look at the IT number, the small number is going to give you the smaller tolerance. Tolerance means, oh, I'm going to tolerate, up to that much, kind of like that, common English word. So tolerance zone, again, just for reading here, it is better we go into the problem so you can see it. So the fundamental deviation is nothing but we combine your IT number, and IT number and then your fundamental deviation together to make your tolerance zone, But you kind of get what the tolerance zone is anyway. And your IT is actually going to give you the magnitude of your tolerance zone, because you have like two things going on in the tolerance zone. One is your IT number and the other one is a fundamental deviation. So what is the magnitude of the tolerance zone? It's just a big word, mathematics, okay, and physics, of course, mechanic, they're all together anyway. We say it's just a value, So you're just dealing with the amount or the value that the dimension can vary, Saying the same thing in different ways, by the way. So the fundamental deviation is going to tell you the position of that tolerance zone, And of course, every time we think about the position of the tolerance zone, is always dealing with the basic sides, because you have the basic sides, usually the midpoint, and sometimes it's not, but the basic sides is always like they're usually in between or at, okay, the limits. So you can understand that the basic size and your limits, the tolerance zone range, they're all connected, okay? It just the way that they're writing in English, it just they confuse you. If you see with the upper limit and the lower limit, your max and min, and then your basic size is somewhere in between or on it, you kind of get it. It's just telling you the same thing here by using the symbols, and a different, of course, name for these definitions. Don't worry about it, just read it, okay? You will get it. Metric tolerance definition, again, we go straight into this shift in the whole system right there, And you have your limits right here, and we're dealing with the diameter, of course, in this system all the time. Fit is right here, Your materials of the parts are right there, that you can see your least or your max. And your upper and lower, upper and lower limits for your hole, and the shafts are also given that for you in this tolerance. So let's see. This is your next exercise, and that is I put it right here, number 6 right there, So you're going to start with your basic sides. So how to calculate, going from the tolerance, which is given here, the limits are given there for you, and your calculation is number 6 right there on your Excel sheet. I give it to you, and you start calculating your basic size and get the common. You have 2.15 or 1.9 for a shift hole system, and you have to get the common point right there. And then of course your UD, and then your LD calculation, which is this one, basic size minus your D max. This is your maximum and minimum limits right there, your upper and the lower. So your upper deviation and the lower deviation, which is right here, and I show you how to calculate it. Yes. So ABS is nothing but the absolute. It's just a formula for the absolute value, because your UD, okay, got to be calculated in an absolute. Okay, this is called the absolute value sign. So when we calculate that, you can see ABS is for the absolute, and you put like a 2 minus 2.2, and you will get 0.2 for the answer. We do the same thing for the LD, your FD, okay, and then your tolerance, yeah. FD is you get the minimum value, yeah. Minimum value from the B from here and here, you will get the minimum value is your LD. Because it's set as so, yeah, your FD as your fundamental, yeah, deviation is right here, yeah. Deviation is smaller of the UD and LD. So this is how we calculate, okay. And in fact, this you're supposed to be doing this calculation by yourself, yeah. But nowadays students are very different because we have to show you how to calculate. If we don't show, then you don't know how to do it. But everything, yeah, that you need to know is given to you right in this, yeah, handout. But of course, I'm also teaching you how to do it and how to calculate it because you have no clue how to do it sometimes at your home, okay. So and then of course we get this as a rounded one for you, and you'll put that into it, okay. So 0.2 and then 0, okay. Your whole, okay, 0.2 is shift and your whole is 0. So here is your whole is 0 and then this is your shift 0.2, okay. 0.2 is your whole and then 0.1. So 0.2 is your whole, 0.1 is your shift, okay. So we do the same thing for the fundamental. Fundamental is just get a smaller number, yeah. So it's just the 0.2 and 0.1. The smaller number is 0.1, so we take 0.1. So here 0 and 0.2, the smaller number is 0, so we take 0, yeah, for FD. So that's go into here. And then we'll have to identify the fit type. So interference again, yeah, you know, you play with your zeros, yeah, less than 0 or equal to 0 or greater than 0, yeah, you identify there are only 4 different fits for that. And of course, we identified that it is A. The fit is the interference because your max clearance is less than or equal to 0, yeah. So here is your max clearance. You of course calculate the max clearance, yeah, by 2 minus 2.1, which is here, yeah. And make sure you write down the maximum, yeah, shift. This is minimum hole, maximum shift, and the minimum hole right there all together. Otherwise, it's going to be very difficult, yeah, for you to write it. These are just a limit, okay? Limit given to you. Where do you get it? You get it from here. Yes. So please study your Excel sheet. I gave it to you. Go, yeah, slowly. Don't erase it. Keep the original so you won't lose. Or you can download it again and again if you want to study. Yeah. And then of course we'll get into metric tolerances. So here we're still in the ANSI, standard limits and the fits. And of course we're using the ANSI B 4.2 1978 R2004 standard. And here is our hole and shaft, and the fit is this. Okay. So this is just a table showing you. See, I told you, don't worry about it. We're going to get back to it when we get to that. Yeah, so here H11, C11 is in this table, okay? So you can see the whole basis is that, and mean like that's so loose running for the fit. Free running, close, sliding, locational, clearance, transition, interference, medium drive, and the force, okay? Depends on how we write for the whole, and then of course don't forget, this is a system between the shaft and the hole, yeah? That fit to each other. So these are tiny little things when you're reading to be able to recognize what you're reading. Alright, then we get into tolerance designing. Alright, the major fit, we're going to deal with the fundamental deviation and your IT numbers. So that's 2, yeah, magnitude and the position. Don't forget that. So IT, again, the amount that the dimension can vary, and we call that the magnitude, yeah. Your tolerance zone size, so fundamental deviation is a letter, the one that we use, yeah, in the chart, yeah, here, yeah, amount and the letters. Establish the position of your tolerance zone, yeah, with respect to the basic size. So your hole is going to be the uppercase, and then your shaft is going to be in lowercase, okay? So hole and then the shaft, yeah? They have letters and also they have value magnitude right there. Then tolerance destination. So fits, we're going to take a look at the fundamental deviation and IT number, yeah? So when you specify the fit, we have to look at the whole, which is your uppercase letter, and the shaft is your lowercase number. Let's see how we can identify that in this example. So here's an example, and when you take a look at it, we see many different things here. Your diameter, yeah, and here is your basic size is for your diameter is 50, yeah, and then here, of course, this is your whole because that's a H, capital, yeah. 8 is a tolerance. Go back to the table and you can read what that is. It comes from the table, how to read it, but you know that this is a whole tolerance zone, yeah, because it's in capital. The small case is your shift tolerance zone, C, yeah, so therefore that's your shift tolerance zone. Of course, they have their own magnitude, which you can go back to your table to look at it, what they mean. And then your D, okay, that's your fundamental deviation, is telling you that. And of course, this is your E, which is your IT number, yeah, so that's a fundamental deviation, and then this is your IT number. It's just telling you, oh, the letter is your fundamental deviation, and then the number is your international tolerance grade number, your IT number E, okay. So this is your magnitude, and that's your position in that hole and shaft or system, okay. All right, the metric tolerances. All right, now we'll get into the basic hole and shaft systems. So when you take a look at that system, you see that you have your metric limits and the fits. They're divided into two different systems. You know, in this systems, you have two different things going on. One is a hole and the other one is a shaft. So when you look at the whole system, you have your basic size, yeah, and basic size is always your whole dimension, meaning like the value of the hole, which is your diameter, of course. So when you think about the hole, we usually make the hole by using a drill or reamer or broach, yeah, or other hole drilling, yeah, tool, whatever that can make a hole. You know, these are just trying to use review how you can be able to drill, yeah, drill the hole. The shaft system, of course, you're going to use your basic size of your shaft, and the basic size again is attached to the shaft dimension, and your shaft dimension is again is the shaft diameter, yeah, so you know that. So shafts are like your rods, yeah, in the mechanical design, of course. Your hole, you have to drill it, but your shaft is going to fit into the hole, and usually it's a rod, yeah. Of course, you can have different types of material for that rod. And space between the hole and shaft is very important, so the type of the material also important, because if you use a metal, then you have to consider the expansion of that metal, so your physics, yeah, is going to also be connected with chemistry and mechanical aspects of it, yeah. Alright, then we'll get into example. So this example, you can see how to calculate on number 7 in your Excel sheet, which is here, yeah. And of course, SH meaning shaft, H meaning hole, yeah. These are the numbers right there. And we're doing the same thing, calculate, yeah, minimum clearance and the maximum clearance, and then you will take a look at the minimum clearance, compare with your 0 to identify the clearance, okay? So that's what we're doing here. Yeah, do the same thing for the other 3, which I have already done it for you here, yeah? All you have to just study, yeah, study them. It's like repeating the same thing again and again. And the next example, again, giving you the yes, you have to determine the limits, tolerance, and type of fit, and you're given this, yeah, standard. So you will use your book appendix to go to read in that table, and you will get the value, yeah, which is going to be this one. Yeah, we do the same thing. MMC, LMC, maximum clearance, minimum clearance, use it to identify the clearance, and we get is a clearance fit, yeah. And we go in and get the tolerance, it's just minus that. Basic size, we calculate, add it up, and divide it by 2, yeah. So that's everything that you need to know, yeah, about this. So here, and that's number 8, which is here, okay. So all the way to the end, okay. And then of course followed by number 9 in the Excel sheet, which is this guy. Yes, and where's yeah, and all you have to do is do the same thing. Yeah, stick to, don't forget it, stick to this standard. Yeah. And where do you get that? In your appendix, in your textbook. Yeah, we can skip the textbook, by the way. Some of the programs or the curriculum is based on the textbook, and I know that it's very some students have issue buying textbook. I also understand how stressful it is. Yeah, but yeah, do everything you can. Library also have like a couple of yes, copies for the textbook, and you can be able to get that. I believe that in my class you'll have it, so make sure you use it and don't sell it back. Okay, keep it. You need it. Then we'll get into selecting the tolerances. Tolerances are very important. I have already told you in the very beginning, yeah, for manufacturing, because tolerance is, it's very important. Without this, it's very difficult for us to be able to manufacture the correct thing, correct parts, right? Correct dimension. So when you think about the cost factor, yeah. So if you play with the tolerance and you reduce the tolerance, your cost for your manufacturing is going to go up, yeah. And there's a serious relationship between the tolerance, how engineers and the drafter make it, and the cost of your manufacturing. So they're pretty much related, and you have to be very careful when you deal with that. You don't want to make the engineer angry, yes, because people with knowledge, if they really want to be bad, they can be so bad, yeah. And the effect is also so. Yes, maybe that's also one reason I believe that they don't want to hire engineers or people who have PhD, or like people who really study, because they know a lot. Yeah, they know a lot. So in the real life situation, they would rather want people who don't know and who will do exactly as told than the people who know. And that's the truth about this world. So yeah, and be careful. Yeah, and when you do your career choices, and also be wise. Yeah, be wise to deal with the people, because the hardest thing in the job is to deal with other people, to work with other people, not your job. Your job is pretty easy, trust me, to do the job, but dealing with other people every day, that's just, oh my gosh, yeah. So make sure you choose the environment and the culture of your organization very carefully before you get into it, so you don't feel miserable, yeah, as you work. It's better to not to have any job than having a job in a miserable place that you feel that you go and work every day. Okay. So when you deal with the tolerance, it can be reasonable. Yeah, be reasonable. Even though this book is writing out, be generous. Don't be so generous. Also, don't be so mean. Yeah, just go with the reasonable amount to play with this cost. Yeah. Again, of course, that's just a business factor, but the most important in mechanical engineering is we have to keep the function of that part, okay, intact. So you can, so also your quality, aspect of the part, your part got to, do what it's supposed to be doing. And when you play with the tolerance, the priority is not this, even if it's very important. Your priority is this, okay? And that will follow after that. So make sure you also, so Japanese companies are very good because they always care for the quality in every material. Every product that they make is the quality is the highest in the world. Yeah, why? Because they target the function instead of that. Yeah, that course will follow. Yeah, as you do. Okay, so that's all. Be careful playing this tolerance, and then function and the cost. All right, three key points right there. And how good are you doing your job depends on the three. Okay. Okay. So here's your IT grades. Just showing you an example, and here's the machine operation. Of course, we're doing all kinds of lapping, so you got grinding, turning, boring, broaching, reaming, so and so. And here you can see the grade from 4 all the way to 11. All right. So the color ones are just showing you where the IT grades fit to the operations right there. Okay. Okay, so when you choose the tolerance, what's the most reasonable or appropriate tolerance? So we usually play with these factors. Yeah? So length of the engagement, your load, bearing load, speed, lubrication, temperature, humidity, material, yeah? And of course your experience, yeah, plays a significant role, and that's why the people in the manufacturing want to hire the people with experience who work there for a long time instead of people with degree, yeah. That's because of this, yeah. So anyway, so these are temperature, humidity, they are environment, we call it environment. So lubrication, yeah, material, yeah, that's the material part. Your speed, your load, engagement, okay, these are all the function stuff, mechanical stuff, of course. So physics and chemistry, everything, yeah, in it all together, along with the mechanics. Tolerance, all right. Now we're going to take a look at the accumulation. Since we're dealing with the tolerance accumulation, you're dealing with, yeah, more parts, yeah, different features, the two features of a part. You have dimension, different controlling dimensions, yeah. And when you think about the tolerance between the two features, you gotta know that the tolerance accumulate. So when you take a look at this picture, you can see, look at that, the distance, yeah. So the distance is here in this example being controlled by a single, yeah, dimension or multiple dimensions. So in this example, see, these are the multiple dimensions stack, yeah. So that's, you can see the tolerance accumulation, because of 1, tolerance 2, 3, 4 right there. Okay, so you can add them up, each one of them, for getting the entire part, yeah, because you have a 1, 2, 3, 4 features on it with different, okay, controlling dimensions right in there. So you have controlling dimensions, and then you have tolerance, yeah, each one of them. So that's your tolerance accumulation. So the most important thing is the distance, yeah, could be controlled by the single dimension or multiple dimension. Meaning, like, you can go the distance from here all the way to here, or you can break it down like this way, yeah. So how are we going to do the tolerance accumulation? So all you have to just add them up, I said it. So your maximum variation, yeah, between the two feature. Of course, you can have like more than two features. Right now, I'm just telling you two features. Then all you have to just add them up, yeah. Add mean like the sum of the tolerances placed on controlling dimension. Mean controlling dimension is the each dimension of that feature, yeah. So if you have two controlling dimension, and you are going to add the tolerances to get the tolerance accumulation. So if you have like many controlling dimensions, then you're going to have a bigger, yeah, tolerance accumulation. So that's what it's saying here. And don't forget, review, you have your stated clearance, yeah, in your dimension chapter. So stated clearance and your implied tolerance, yeah. Stated tolerance and implied tolerance, same as your dimension, okay. So what it's saying here is for tolerance, even if you don't have a stated, yeah, tolerance, you might have like an implied tolerance. If you don't have an implied tolerance, you might have a stated tolerance, yeah. So make sure which tolerance type you're dealing with when you do the tolerance accumulation. So the first one is like this, and this is pretty perfect. We go 1, 2, 3, 4 feature right there. Yeah, we also go one a big feature right here. And here is not very good because you go 1, 2, 3, 4. It looks like the same to you, yeah. But when you read it very carefully, you can see, look at that. There's a 40.1, yeah, 20.1, 30.1. So see, it's different. Yeah, you have a decimal in the values for this case, and the other one doesn't have it. Yeah, you have the exact dimension right here. Because this was kind of like not perfect like this. Yeah, this one is a perfect because you can add it up, all of it, and you will get to 70 here. And here is like you have like a 70.3. Yeah, a little bit of it. Yeah. It's just showing you different ways of writing it, but don't do this. It's not very good, and you try to stick into, yeah, this type of method. So now we'll get into and okay, like how are we going to calculate that tolerance accumulation? What is it? So the question is asking you give me the tolerance accumulation from surface A, which is this one, and surface B is this one. So you have three feature. So when you look at it, you have a dimension, and then your tolerance right there. You have 1, 2, and 3. So you add them up, it's set, So you add it up and you get 0.3, And the next one, the same thing. Hey, give me the tolerance accumulation between a surface A right here and then the B. So you're like, oh, okay, so from here to here, now how am I going to do it? So now you're not given directly like this, okay? You're given what C with the ranges like that. So you still have to get this, and that, okay? So it says, so from here to here is 0.1, from here to here is 0.1, so you got to calculate what that is, okay? Also, you have to calculate this, and then you have to calculate this part, so make sure that you subtract, that from here, subtract that from there, subtract that from there, in order for you to get it. And when you add it up, you're going to get 0.2. And some student might argue, yeah, okay, in order for me to get this, I would just minus, this from here. Yes, you can do that. So if you minus this from this, you get like a 0.5, 0.05. And then of course, when you minus, this from here, then you're going to get the 0.05 here as well. And then when you minus that, you're going to get 0.05 here. So, but altogether you will get like 0.15, But when you round it, you still got that 0.2 anyway, And we do the same thing for this, So now surface again between A and B from here to here, you can go subtraction like this, or you can just straight write it down, 0.1 right there, because it's given to you there anyway. Okay, so formatting tolerances. We're going to follow the ASME 14.5M standard, and you've been seeing this standard all the time, You should be able to get it by now. So metric tolerances, the first one is your standard fit tables. This is just showing you how you write, standard fit table tolerance, metric tolerance like this. So you can see the diameter is like that in your lower upper, And here also we write it this way because or that way, So you have 1, 2, 3 different ways of writing this standard fit of tables. And this one is a unilateral tolerances, and we write it this way, okay? You can see there's a plus or minus, kind of like a plus or minus thing. You have 0, and then without a plus or minus, and then you have value with a plus or minus, and that's your unilateral tolerance because one of the limit is 0, so we call it unilateral. By you have both, so therefore we do plus or minus values, Of course, you don't do like this. So what's the difference between that? Is this, you have to fill a 0 at the end and don't leave it like that, okay? Limit dimension, again, write this way. Do not leave it like this without zeros, So limit dimensions, the most important thing is they have the same number of decimal places. So you have 2 decimal places here and you have 2 decimal places right there. Basic dimension with a tolerance, we write it this way, okay? And don't do like this. We're not filling in the 0 right here, We're just going with a straight 45, and then your decimal is going to be shown in your tolerance range right there, Then we have our unilateral and bilateral tolerances, okay? Again, here, don't forget to put zeros because they have the same decimal places, And this is wrong, and it's because you forgot, See, there's a little 0 right there. I'm showing that to you. You cannot get everything, so you just have to, try to study that little by little, because it's very confusing, right? Each one of them here. And limit dimension, again, don't forget the 0 because they have to have the same number of decimal places, And the last one is this. And don't forget here, yeah, you have 3, yeah, so therefore keep the same again number of decimal places. Angular tolerance, we write it this way, okay, and don't forget 0, 4, yeah, but they have to have the same decimal place. So because when you carefully look at it, this is a 1 decimal place, so therefore you have to put the 0, yeah, for the significant figures, right? So this is wrong because you have a 1 decimal place right there and you forget to put the dot 0 right there. Alright, so that's it for today, and I have an exercise for you and you can do that. If you can finish it in class, I'll be very happy. If you cannot, you can also do that at home and bring it back next time, okay? Alright.